Hey everybody, I'm going to open up our visualizer. This is the first video that goes with the Equilibrium Part 3 PowerPoint. There is our screen, our overhead. All right. So the big thing that we're going to talk about in this module is an ice table, or sometimes it's called a rice table. But before we start something new, I always like to review a little bit. So this first video from Equilibrium Part 3 are what I call problems of the day or review questions. So that's on our next slide. Okay, so we're given a balanced reaction and we're given an equilibrium constant value, and we're asked, is the reaction reactant favored or product favored? We're given NH3 plus water forms ammonium and hydroxide. Now, you'll usually see this written as one ionic compound that's made of two polyatomic ions. I just wrote it out separately because it's easier to see the proton transfer. And pretty soon we'll be talking about acids and bases. Okay. What's really important here is the number. The equilibrium constant equals 1.8 times 10 to the negative 5. This is all the information I need to determine if something is reactant favored or product favored. Remember, if K is greater than 1, it's called product favored, because our ratio for K is products over reactants. When K is greater than 1, that means we have a larger amount of product, the numerator, and a smaller amount of reactant, the denominator. This is a really small number. That negative exponent is a dead giveaway. So in this case, K is less than 1, meaning we call it reactant favored. We're still using that ratio for K. K is always going to be this ratio of products in the numerator and reactants in the denominator. Okay, so because the value of K is less than 1, we can call it reactant favored. We don't even need the reaction. And this will depend on temperature, so this might even be product favored under some different conditions. So we just look at that value. All right, our next problem will take us maybe a minute. For the above reaction, you take a sample after some time and find the concentration of ammonia is 1 times 10 to the minus 3 ammonium, the polyatomic ion, is 5 times 10 to the minus 3, and hydroxide is 3 times 10 to the minus 5. These are all concentrations in molarity. I don't have a value for water. If we look back at water, the phase is L for liquid, pure liquid. So we don't have that in our K expression. Let's go ahead and write our K expression. And then I'm going to plug these values in. And I'm going to determine, do I get that value for K? The value that was given in problem 1 is 1.8 times 10 to the minus 5. So what we're really solving for is something we call Q, which is this same equilibrium constant expression only Q is at any time. When it's equal numerically to the value of K, we can then say it's at equilibrium. So we're going to just plug these numbers in and ask, does Q at any time equal K at equilibrium? Okay, so I'm going to plug in these values. 5 times 10 to the minus 3 times 3 times 10 to the minus 5 divided by 1 times 10 to the minus 3. Okay, so 5 times 3 is 15 divided by 1. Negative 3 plus negative 5 is negative 8. Minus negative 3 is negative 5. So the numerical value for Q is 1.5 times 10 to the minus 4. Does that equal 1.8 times 10 to the minus 5? No, it does not. So, no, it's not at equilibrium. Because when I plug in the numbers into my K expression, I do not get that numerical value for K. That's it. All right, practice this one a lot. You're definitely going to see it.